Okay, so just, so I hope it's audible on the Zoom. I guess. Okay. If it's not, huh? Yeah, if it's not, you can unmute it. Let me know. Is it audible, Geeta? She's muted. Okay. Anyway, if it's not audible, you can call me on my phone also. She's saying something. I don't know if our audios are.
Hi, Amri.
Oh, hi. Yeah. Can you hear me?
Yes. Yeah.
Okay, great. Okay. And so feel free to stop me and ask any questions.
Yeah.
Yeah. Which goes for anybody on Zoom. So, yeah, so I'm going to talk about something called Koszul duality. And this is partly based on joint work with Geeta and Shraddha. And then I've been trying to think about this again with Tirtharaj. So we'll see how this goes. So, so firstly, let me talk about polynomial representations of GLNC. So a polynomial representation of GLNC is a group homomorphism from GLNC to some GLW, where W is some vector space, and it must have the following property that for every vector V in this vector space W, and for every linear functional xi, so I'll use tilde to denote the linear dual of a vector space. So this is just linear maps from W to C. The function G goes to xi of rho GV is a polynomial in the entries of the matrix G. Okay, so typical example would be you could take W to be Cn itself, in which case this would just, you could take this to be the identity map, right? And then the these will just be linear functionals on in the variables. Okay, so if you take V to be Ei and xi to be Ej, then this will be either the ijth or the jith entry of the matrix G itself. But you could also take, like, you know, wedge DCN, sim DCN, and more generally we'll say that there are certain other functors called W lambda Cn. So this is the kind of representations that we are going to be looking at. And for such a representation, you can define the character of rho. This will be a polynomial in x1, x2, xn. This will just be the trace of rho evaluated at the diagonal matrix on the vector space W. So the trace just evaluated at this. And because if you permute the diagonal entries, you get a conjugate matrix. It would correspond to conjugation by permutation matrix. This is going to be a symmetric polynomial in those n variables, right? So, yeah. And we'll be focusing on homogeneous polynomial representations of degree D. Then we would require that this is a homogeneous polynomial of degree D, right? So this sim D and wedge D, they are homogeneous of degree D. If you work out if you write down a basis for this, for example, write out the matrix entries, they'll be homogeneous polynomials of degree D. Okay, so some facts about this kind of representation theory. So firstly, every polynomial representation is a sum of simples. Then every simple is actually homogeneous. So every polynomial representation is sum of homogeneous polynomial representations. And then the simples of degree D, they correspond to partitions lambda. So I'll use this notation P and D. This denotes partitions of D with at most n parts. Okay. Any? Yeah. Yeah. So you say that a representation, polynomial representation is simple if it is it has no invariant subspace. And W is a finite dimensional complex vector space. Yeah. And for this, corresponding to this, you have a representation which I'll call W lambda, but you also need to specify what this GLN is. So it's often denoted W lambda Cn. It actually is a functor, so that's another reason for this notation. So I'll call this rho lambda W lambda Cn, this representation. And what you have is chi of rho lambda is just the Schur function. Right, so this Schur function in n variables vanishes if lambda has more than n parts. So that's consistent with this, that these are the Schur functions in n variables. So that's the basic theory of these kinds of things. It goes back to the time of Schur. And one thing I want to also define is the contragradient representation. So W lambda, this is the contragradient, and now it's sort of inconvenient to take inverses. So I'll just think of the contragradient as a right representation. So so xi, if xi is in W tilde, xi dot g, well, that should be another linear functional if you evaluate it at this. So maybe, yeah, xi of gv, where this is the action by rho lambda. Right. Yeah, on the right. Xi acts on the right of g by acting on the left of v. So that's the, yeah. Okay, so this is a right representation. Okay, that's the basic polynomial representation. So okay, and then let me also remind you about representations of the symmetric group. So that's section 2. So so if you have a representation, actually, why do I even need this? So sigma lambda v lambda is an irreducible representation of SD for every lambda partition of just D, no condition on the number of parts. If there's only one argument, it's the second argument, or PDD if you wish. And Okay, so what's the connection between these two? So here's a connection. So, so you look at, suppose W is a polynomial representation of degree D of GLD. So I'm taking n equals D now. Okay, so then I can talk about the all ones weight space. W all one. So this just denotes the vector 1, or we could call it W maybe 1 to the n. So this is defined as V in W such that rho of x1 xn V is x1 x2 xn times V. So the eigenspace with eigencharacter x1 x2 xn goes to x1 into x2 into xn. This is called the all ones weight space because this is the all ones character. It's just x1 to the power 1, x2 to the power 1, xn to the power 1. Sorry? No. So here we are just taking W all ones. W21, the 2-1 weight space. Okay, but this one is a representation of Sn. This is what? Of degree D. Yeah. Degree D. Yeah. Homogeneous. Yeah. No, just x1 squared x. Yeah.
You want it of GLD, you say?
GLD. Yeah. Yeah. So D and
What
N
have you
are
written?
now. Oh, this should be D. 1 to the D. Yeah. Everything is D. N is equal to D. So this is, for example, if you just take sim DCD, then what is the all ones weight space of that? So if you think about it, what is sim D CD? So sim D has a basis given by multisets of the set 1 to D of size D. Right? I mean, generally sim D Cn is multisets of size D of the set 1 to n. And now you're asking for a multi-set which where each of the elements occurs exactly once. So this is just one dimensional. It's spanned by the tensor E1, E2, Ed, the symmetric tensor E1, E2, Ed. So it's one dimension. And this is a representation of the symmetric group SD, because if you were to just take a permutation matrix, it would preserve this. You can easily check. Okay, so if something has weight x1, x2, xt, then any permutation rho W of V would also have weight x1, x2, xt. So that's yeah. So you starting with a polynomial representation of GLDC of degree D, you get a representation of SD. So what's the connection between these things? So you can also do a slightly more interesting exercise. So if you're given a partition lambda, you can talk about sim lambda CD. So by definition, this is this sim lambda 1 CD tensor sim lambda 2 CD and so on. And if you ask what its all ones weight space is, then this sim lambda CD, let's say lambda is a partition of D, then this will be homogeneous of degree D, and its all ones weight space will be what I call Cx lambda. What is this? So this x lambda is all partitions S1 union S2 of the set 1 to D, all set partitions such that cardinality of Si is equal to lambda I. So it's all set partitions of shape lambda, and SD acts on this by permuting the elements of these sets. So this is a permutation representation, and this is so you can easily show that this is the same as this. This is also the induced representation from the trivial representation of the Young subgroup. So this is what is called the permutation representation of SD. So what you see is that the all ones weight space, sorry, this should be all ones weight space. So the all ones weight space of sim lambda is this thing, and it follows from just this that the all ones weight space of you can easily prove it from that if you take lambda is a partition of D, then if you take W lambda CD and then take the all ones weight space, this is as a representation of ST, this is B lambda. Okay, so you can construct the representations of SD from the degree D polynomial representations of GLDC. V lambda is the irreducible representation of. Yeah. Yeah. And the proof is actually very simple. You just have to prove this thing. And now these things form a basis for the Grothendieck group of the category of polynomial representation. Every W lambda can be written as a virtual sum of these SIMDs. Every representation of SD can be written as a virtual sum of these things. And the relationships are exactly the same. So the Frobenius characteristic of this is H lambda, the character of this is H lambda. So anyway, so it can be proved from there very easily. Okay, so that's okay. So now let's move towards something called Schur-Weyl duality. So I'll go to Schur-Weyl duality via something called Howe duality, or yeah. Okay, so firstly we'll start with Howe's GLM GLN duality. So what is this? You take CM tensor CN. So this is a representation of GLM cross GLN. Right? And then you take sim D of this. Okay, it turns out that we can compute what this representation looks like by computing its character. So if you think about it, CM tensor CN, maybe it's better to think about this as CN, identify CN with its dual, and then you can think of CM tensor CN as the space of maybe you should identify CM with its dual, then CM tensor CN will be the space of M by N matrices. Right, so this is the same as M by N matrices over C. So this SIMD is just yeah, so it's the dual space of polynomials, homogeneous polynomials of degree D in M by N C, right? So this is equal to dual space of homogeneous polynomials of degree D in Xij, 1 less than or equal to I less than or equal to M, 1 less than or equal to J less than or equal to N. And so if you have something like the dual vector, so here a basis is integer matrices M by N, integer matrices summing to D. For example, if you have the matrix 1, 1, 0, 2, 3, 1, this corresponds to the monomial x11, x12, x21 squared, x22 cubed, x23. Right? So every homogeneous monomial of degree D can be just represented by an integer matrix whose entries add up to D. SIMD is the dual of the polynomial. No, polynomial, what are polynomials of degree 1? They are linear functionals. Dual of SIM. Yeah, polynomial is the dual. Oh, Xij is already dual. Yeah. Sorry. Yeah. Thanks for pointing that. Sorry, I got confused. Xij is already a linear functional on matrices. That is, you take the matrix to its ijth entry. And we call that Xij, and then, yeah, okay, great. That makes life even simpler. So this is SIMD is equal to, yeah. Thanks for the pointing that out. I was, no. Xij is in SIM1 star. Yeah, you have to put the MN star. Huh? No. So what is polynomial of degree 1 in Mn? Xij? Polynomial algebra is in B star. No. One sec. What is Xij? Yeah. So it's the ijth entry, right? Now, what is a polynomial? Okay. Yeah. Okay, whatever. I don't care. The point is that we can compute the character of this. So if you're given a basis vector corresponding, so let's take for every, let's call this matrix A. So you're given a basis vector xi A, and you look at what is the action of, so in GLM you have like x1, x2, xm, and in GLN you have y1, y2, yn. Let me write it properly. So if you ask what this will be, then what you'll get is x to the r of A, y to the c of A, xi. So this basis vector will be an eigenfunction for the action of these diagonal matrices, and the characters are the row sums of A and the column sums of A. Okay, so this representation has character of SIMD MNC is equal to sum over A in matrices, n by n matrices summing up to D, x to the RA, y to the CA. Okay, this is a homogeneous term in the oil, what is it called? Product of. So there's this yeah. So here, I guess one of the Littlewood identities, but it also follows from RSK correspondence. Actually, this should be M by ND. M by N matrices that add up to D. Matrices with at most M parts and at most N parts. I mean, with minimum of Mn parts. Partitions of D with at most minimum of Mn parts. S lambda X, S lambda Y. Yeah. Yeah. This will be a by character. I mean, it will be a character into M, M, and C. Thanks. Yeah. So this is what you get. So this, what this implies is that sim D of Cm tensor Cn is direct sum over lambda in running over appropriate things, W lambda Cm tensor W lambda Cn. This is sometimes called Howe's GLM duality. So this lovely paper of Howe in a volume called the Schur lectures, where he does a bunch of these kinds of things from the point of view of invariant theory. So this is a slightly different approach to those same results. Worth reading. So there are some other dualities of this kind which he gets. But yeah, you can prove it using the RSK correspondence. And why did I do this? Well, this is one way to get the decomposition which gives Schur-Weyl duality. So what this implies is sim D Cm tensor Cn, and now I'll take the all ones weight space in just the one set of variables, the M Cm X, huh? Yeah, it's the guy whose character is a Schur function S lambda. So if you take this, then what does this say? So I have to take this guy's weight space, right? So let me just do this here, D here, D here. Or do I want to maybe do it D in the second? Okay, let's just do it like this. Sim D. Yeah. Okay. So what will I get? I just have to replace this W lambda Cn by V lambda. So I'll get some.
Amri, some problem is there. I couldn't see the board.
Ah, good, it's come. Okay, Geeta, you can see
Yes,
color. Oh,
thank
okay.
you.
Okay.
Yeah.
Okay, good. So that's the decomposition. Now, what is this? Turns out that if you think about what this is, so this is Cn tensor Cd. So it has a basis given by, in general, this has a SIMD Cn tensor Cd has a basis given by matrices which sum to D, which are n by D matrices. Uh, yeah, this is a GLN cross GLD representation. Now it's only the GLD part. Yeah, only in the second part. Okay, so now a priori, what is this? This is matrices A, which are n by D and sum up to D, right? If I don't take the all ones weight part. If I take the all ones weight part, then what I'm saying is that each there are D columns. Each column must have only one the entries sum up to D. So this is a matrix whose entries sum up to 5 plus 3, 8. So now if I want the 1D, then that means each of these columns must sum up to 1. Yeah. First, I looked at a GLN cross GLD representation. Then from that, I constructed a GLN cross SD representation. And so now I'm saying what that is. So the GLN cross GLD representation is just SIMD Cn cross CD. That corresponds to matrices, all matrices which sum to D. The all ones weight space corresponds to matrices whose each column just sums to 1. So that means that each column just has one entry non-zero, which is between 1 and n. And so it turns out that, can you guess what this is? Well, I guess you may have, not this, sorry, this all ones weight space. This turns out to be Cn, tensor Cn D type. Because you're just looking for matrices like this, each column sums up to, so you have 0, 1, 1, 0, 0, 1. This will correspond to the vector E1 tensor, E2 tensor, E1 tensor, E2. Because here the GLN action is just on these things. So, so what we are saying is, finally, the conclusion is that this, let's call this TND. So TND is defined to be Cn tensor with itself D times. And what we are saying is that this is a sum over lambda in PND W lambda Cn tensor V lambda. So this is the decomposition of the tensor space as a GLNC cross SD representation. Okay, and from here comes Schur-Weyl duality. So
So, Amri, in this case, n should be bigger than or equal to D, right? You don't need that assumption.
no, it doesn't matter. The thing is, if n is smaller than D, not every partition will occur. This factor will become 0, and so you'll only get.
Okay.
So you don't need n to be bigger than or equal. Like you can even take D equals 1. then what do you get? You get Cn is just Cn tensor trivial representation.
Okay.
It still works.
So on the left, if P at permuting tensor.
Yeah, here SD acts by permuting the tensor factors because that's inherited from the action of SD on C to the power D. Yeah, yeah. So actually, maybe it's I should have yeah. Yeah. Okay, so that's Schur-Weyl duality. I mean, I'm sketching the general ideas. It's not difficult to fill out the details. And now, if you ask, what happens if I take Hom SD from V lambda to P and D? Okay, so let's work this out. So we know the decomposition of T and D. So we get Hom SD from V lambda to direct sum over mu over whatever it runs. W mu Cn tensor V mu. This sum is over, I guess, P and D. Right? I've just used this decomposition. And this is so Hom. So the SD has nothing to do with this factor. So I can just write this as Hom SD V lambda sum over mu, Hom SD V lambda V mu tensor W mu Cn. Mu is in P and D. Right? Now by Schur's lemma, this is either C or it is 0. So we'll just get one term which will survive, which will be W lambda Cn, provided lambda W lambda Cn, if lambda is in P and D, and 0 if lambda is not in P and D. But I like to think of W lambda Cn to be 0 anyway if lambda is not in P and D. So I'll just write W lambda Cn. Well, in general, it's W lambda Cn. So what you get from the representations of the symmetric group, you can construct representations of GLN. And you can also go the other way. You can construct from representations of GLN representations of symmetric. So this thing is the bimodule which gives an equivalence between these categories, provided, as Geeta was saying, n is greater than or equal to d. If n greater than, so this is called the Schur functor. So this is called S, or maybe the Weyl functor. I don't know. S. So if n is greater than or equal to d, S is an equivalence of categories. So that's yeah, this whole Hom thing. So this is a contravariant functor, is it? Okay. Not great, but anyway. So maybe we could have done it the other way around. Then we'd get the dual. Anyway. Yeah. 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 And every object in the every representation of GLNC is isomorphic to some object in the source category. And what else? the simple objects are the same basically for semi-simple categories. So yeah, but for non-semi-simple categories, you have to be very careful. So it's not that these categories are isomorphic. There's a correspondence between the simple objects of the representations of ST and that's called Schur-Weyl duality. So this is one functor. I guess you can also use tensor products to get another functor and so on. But the reason I wanted to do it this way is we'll now come to the Schur algebra. So something. Okay. Yeah, I think a lot of people will scold me for. Okay, so now which section are we at? So now we talk about the Schur algebra. So it's defined as so this is one way of thinking about the Schur algebra, just the ST endomorphisms of tensor space. So if we expand this out, what we get? We get Hom over ST, and we know what this looks like. This is sum over lambda, W lambda Cn tensor V lambda, comma sum over mu, W mu Cn tensor V mu. Right, and so as before, we can write this as Hom sum over mu lambda Hom ST V lambda V mu tensor Hom C but by Schur's lemma, this is just sum over lambda in P and D which we can also think of it as. So this is just end of W lambda Cn, right? The ST action is only on this part. Yeah. So now this will give us. We can think of this as W lambda Cn dual tensor W lambda C. Right. So this Schur algebra turns out to be this. And this is actually a bimodule for GLNC cross GLNC. And this is also a bimodule for GLNC cross GLNC. GLNC acts on this on the left and on the right by precomposing and postcomposing. And this GLNC acts on the right over here and acts on the left over here. So this is also GLNC. GLNC. Okay, so turns out that there's another description of the Schur algebra which coincides with this one. So So let's say we have this poly D in the variables x, I, j, 1 less than or equal to I less than or equal to m, 1 less than j less than or equal to n. And yeah, and we take its dual space. That is linear functionals on polynomials in xij. Okay, this is definitely. So so you can define a multiplication of this. If you have omega and nu, which are linear functionals on polynomials, then given a polynomial of degree d, what should this be? Well, it turns out that this is just, so you can think of this f. So now you have one set of variables x comma y, but let's make it two sets of variables. I guess I want n here, both of square matrices, n by n matrices. So this x is n squared matrices, n squared variables, y is n squared variables, and xy is just matrix multiplication. So totally this has n by, this is an n by n matrix whose entries are in two n squared variables, the x1 xij's and the yij's, right? So this is a polynomial in the xij's and in the yij's. Polynomials in xij's and yij's can be thought of as the tensor square of, well, let's not put d here. So I can act by omega tensor nu on this. This is bilinear, so it will actually be degree d in each of the sets of variables. So I can act by that, and this actually is just resolves into a complex number. So this is this gives me a multiplication rule. So first you evaluate nu with respect to the y's, you will get a polynomial in x, and then you evaluate with respect to the x's. Okay, it's not very important what this is. I'm not going to use it much, except to say that this algebra is isomorphic to the Schur algebra SNE. And this result essentially goes back to Schur, and what it implies is that the category of polynomial representations of degree d of GL and C is isomorphic. I'm going to write equal to here, which means natural is isomorphic. That is, there are functors going both ways whose inverses are the identity to S and D, the category of S and D modules. So let me explain how you get these functors. No. So let me explain how this works. So suppose you have a representation rho of GL and C. Okay, so I want to define what rho tilde of omega is, where omega is in S and D, right? So I need to tell you what happens to rho tilde omega of V for some V in the representation, for which it's enough to tell you what happens when I evaluate a linear functional on that. Okay, so I must tell you for every xi in W tilde V in W. And well, there's only one way to put all this information together. Remember that we had a polynomial which was G goes to xi of GV, right? This is a polynomial in those variables xij, the entries of G. So then what you can do is this omega is a linear functional on that. So this tells me given, sorry, I need a rho g somewhere. So this was a polynomial function of degree d. This is a linear functional on polynomials of degree d, so it's a complex number. And to go the other way, well, you have this delta g belonging to S and D. What does this do? Delta g of f is just f of g. Evaluation of the polynomial at g. This is the Dirac delta function, literally. And so if you're given rho tilde, then you can say rho of g is rho tilde of delta g. So you can go from rho to rho tilde using this formula, and you can go from rho tilde to rho using the delta function. And this makes every representation of degree d automatically an SND module, and every SND module in turn is a representation of GLNC. So the spaces are in fact the same, okay, but there are these two. So these are, so you can either think of a representation or you can think of an SND module, and this is an isomorphism of categories. Okay, so you can recover the representation from the corresponding SND module. You can recover the SND module from the corresponding representation. That's the dictionary for going between them. So that's the equivalence. Okay, so something more I want to say here. Okay, so now finally to the alternating Schur algebra and Koszul duality. So we Geeta and I were actually interested in this question. What is this algebra? Instead of SD, I'll look at end AD, end, and we call this the alternating Schur algebra. Okay, now it's not difficult to show that this algebra has a Z2 grading, in the sense that AS, I'll sort of drop the N comma D because it's getting very cumbersome. So maybe I'll write it just this time. ND is SND, right? Every SND is contained in ASND because I've reduced the group, right? But there's something else, and it has a complement which I'll call S minus ND, where SND is the usual Schur algebra. So I can just say it's HOM SD TND to TND, and S minus ND is HOM SD TND to TND tensor sign. So this is the sign character of SD. This decomposition is actually a special case of a very general thing. In general, suppose you have a representation of SD on some vector space V. Then you can look at VSD, the SD invariance. This will be V0 plus V1, where V0 is the the AD invariance. These are the vectors which are invariant under the action of AD. V0 will be the SD invariance, which I'll write as this: V belong to V such that WV is equal to V for all W in SD. And V1 will be V belongs to V such that W dot V equals sine of W times V for all W in this. Why is that? Well, if you look at the AD invariant subspaces, it has an action of SD mod AD, which is just C2. This is the +1 eigenspace and this is the -1 eigenspace. So that's what's happening here. The SD invariant, so the AD invariants are the SD invariants and the ones which are sign twisted invariant, and that's just this T and D tensor epsilon. So we have this algebra is a sum of two things here, and this is a algebra grading in the sense that if you multiply two things here, you end up back here. This is a sub algebra. If you multiply something here and here, you end up here, and if you multiply two things here, you end up here. So it's a Z2 graded algebra. Okay. So
If you take 4FD,
mhm.
it's tensor for not in FD.
No, it's not. But I'm not doing any such thing. Sorry, SND is just this SD. Yeah, actually, here this is just as vector spaces. We are not thinking. This is a representation of one copy of GLNC, and this is a representation of yet another copy of GLNC. Now, you could take a diagonal action, and that would be a representation of GLNC of degree twice the degree of. But what? I don't want to think of the diagonal action here at all, not of GLNC. Yeah, two copies of GLN. Okay, so that's that's the alternating Schur algebra. Okay, so let's see what the decomposition of S minus. So this S minus ND in particular is an SND cross SND bimodule, and therefore it's a representation of GLNC cross GLNC. Right. So it's got a right and a left representation of GLNC. So where should I? Because I'm multiplying on the left and multiplying on the right. Left multiplication of S minus. So if you take something in S minus, you can multiply it on the left or on the right by something in S. So that is now, so S minus ND. So this is Hom ST, and then we have direct sum over lambda W lambda Cn tensor V lambda comma. Let me create some more space here. Sum over mu W mu Cn tensor V mu tensor epsilon, right? What is V mu tensor epsilon? It's V of mu prime. Right. So that is that. And so as before, if we expand this, what do we get? We get sum over, and so here lambda is in P and D, and here mu is in P and D. But let's replace mu by mu prime. So then we'll be looking at lambda in P and D such that lambda prime is also in P and D. So these are partitions that fit inside an n by n square. And what do we have here? We have mu prime. Yeah. No, sorry. So lambda is in P and D. I'm replacing mu by mu prime. So I'll get V lambda V mu tensor Hom C W lambda Cn W mu prime Cn, because I replaced mu by mu prime, right? And by Schur's lemma, this is summation lambda in P and D, and lambda has also to be lambda prime also in P and D. So lambda such that lambda and lambda prime are both in P and D of, and by Schur's lemma only one term survives here. Hom C W lambda Cn W mu prime hence Hom C, yeah. Or I can write it as W lambda Cn dual tensor W mu prime. This is a tensor over C. Lambda prime, I'm sorry. So this is the decomposition of S minus N. Okay, so it's just this, and this is as a GLNC cross GLNC, representation of GLNC cross GLNC. So this guy is a right module, this guy is a left module. No, you just take the first, take the lambda. So there's a term for each lambda. It will die unless mu is lambda prime. Maybe let me write it like this. Correct. If they are both, yeah, and they will both be in the thing, yeah. You'll definitely get both of them. Okay, so finally we come to section 6, which is Koszul duality. With apologies to Henning Krause. dW is defined to be S minus ND tensor over SND of. So suppose W is a representation of GLNC, a polynomial representation of GLNC of degree D. Then I can think of it as an SND module, right? And then I will take this bimodule and tensor with that. And that's defined as Koszul duality. So let's see what this does to W lambda. So now we know what this SND, S minus ND looks like. It looks like sum over lambda, W lambda C tilde tensor W lambda C. Maybe I should write mu here because there's a lambda there, right? And then I'm taking this whole thing. I'm actually taking this. This is the right action, right? And I'm tensoring this with over SND with W lambda Cn. Right, and now you use Hom tensor duality. Huh? There's a prime somewhere. There's a prime here. Or there, doesn't matter. Okay, so, huh? Cn, yeah. X. So now if you look at what is this W lambda tilde tensor, this is the part that is the right thing. This is just get carried along, right? S and D of W mu, right? By Hom tensor duality, this is Hom S and D W lambda tilde W mu tilde. Right, so but these are both right modules. Okay, but this is delta lambda mu times C by Schur's lemma. So the only term that survives here is the one where mu is equal to lambda. And so this is W lambda prime. So that's Koszul duality. And that's all I had to say. The Frobenius characteristic, it's actually the character, yeah, it's S lambda X, S lambda prime Y. And this is your favorite degree D homogeneous part of 1 plus Xi Yj. Prime. Yeah, tilde, okay. Can still take the character of a right module. So it's again S lambda for the right action. No, I defined it to just be a right representation. So then it's a polynomial representation. I didn't take inverses. Yeah, but I didn't take any trans. I thought it's easier to just keep them separated, not mix them up. So this actually is a very interesting question because you get S lambda times S lambda prime, and you can show that the dimension of S minus n is the number of 0, 1 matrices, n by n 0, 1 matrices adding up to D. And the dual RSK correspondence then gives this decomposition. So you can also prove this decomposition of S minus ND combinatorially. For S and D, the Wedderburn decomposition comes from the RSK correspondence. For the bimodule S minus ND, the bimodule decomposition comes from the dual RSK correspondence. And there should be some more interesting sort of combinatorial games to be played with Koszul duality, RSK correspondence, dual RSK correspondence, and cellular bases and so on. And that's something that I hope to explore at some time in the future. So we can. I don't know if there are any questions on the Zoomers.
No questions.
Basis. Integer matrices summing to D. Yeah, so it has the integer matrices and the 0, 1 matrix. Well, you shouldn't think of them as, yeah, another copy, yeah. Summing to D. Yeah. Both, each of them. So the, yeah. What is? Yeah, yeah, this is the omega. So we all know what is the thing for SD representation, right? It's tensor with sign. But then what is it for representations of GLMC? So that's a more subtle question. And so Geeta and I were working with this alternating Schur algebra, and we asked Shraddha, and she said there's something called Koszul duality defined by Henning Krauser. His definition is different in the sense he doesn't even work with representations of GLMs. He works with the category of strict polynomial functors and somewhat abstractly defines some functor called Koszul duality. So, but because we were looking at this alternating Schur algebra, we came up with this thing.
So this is an explicit Koszul duality.
I guess, yeah, in a sense, yeah. The explicit in the sense, okay, we are giving you a bimodule for which we can describe a basis and the structure constants, and you tensor product with that. But maybe there's more to. Okay, so here's the thing. This is a very important point that there's nothing special about. So you can always suppose you have algebra A. Suppose you have an algebra AS, and AS is S plus S minus. Then you can define a duality on the S mod. By defining that D of W is S minus tensor over S W. So this gives rise to a functor from the category of S modules to S modules. And now what you must do is, suppose you take this S minus, this is an S bimodule, right? And if you find that this has a decomposition like this of some function of lambda, then this duality will take W lambda to WF lambda if this is a multiplicity free decomposition. And you can make this a little more concrete if you have G and H is a subgroup of index 2 in G. So this is where the other types you can talk about something. Then if you define S to be end G of something, and you define AS to be end H of something, then AS will again have this decomposition. And this you can show that this, so you're looking at, so maybe I'll explain this. It's worth explaining more carefully because we are interested in generalizing this. Index 2, so this is the, sorry, is the other way around. Sn. So this is the bigger algebra. Then you can still write AS as S plus S minus, where S minus is Hom of the big group T comma T tensor epsilon, where epsilon is the non-trivial character of G mod H. And yeah, and then you will still get this thing that so now since S is NGT, the irreducible representations of S correspond to irreducible representations of G that occur in T, right? And in fact, the dimension will be the multiplicity. So the multiplicity spaces for the irreducibles of G will be, because, so T is, so suppose T is just V lambda raised to F lambda, then this will become, S will become sum over lambda, F lambda by F lambda matrices over C. So the simples will be W lambda equals C raised to F lambda. And what you will get is that this Koszul duality will take, so suppose I say that V lambda tensor epsilon is V lambda prime, then the same proof will show that Koszul duality D of W lambda is equal to W lambda prime. Always the case. So it's not just in this case, but in general, D of W lambda will always be W lambda prime whenever you have this setting. So you could take here, for example, the hyperoctahedral group. Here you could take the demi-hyperoctahedral group, that is Dn type, Cn type, and you could still define. So take your favorite tensor space. And
with all this, it's not really used that C is the wide group of your
no, actually, for the general thing, you don't need any of that. This is pretty general, right?
No, the symmetric group is not the symmetric, the wide group is symmetric GLN. That symmetric group you didn't consider. You consider the other symmetric group.
Remember, there were two ways in which I connected them. One was to take the all ones weight space. So there we are really thinking of SD as sitting inside GLD. But SD is not sitting inside GL and C anyway, right? D and N are different. So that is not, but I don't know what to say to the Lie theory people. I mean, yeah. So
I just want to know what lambda prime is.
yeah. So then you have to have some sort of duality, and then in the dual side it should be tensor with some character of order 2. So maybe we can try to formulate. So this is one advantage of this method over Krauser's original method, that it will generalize to a lot of other situations. Yeah, we are done. Yeah, thanks. I mean, thanks for the reminder. Yeah. Or thanks for rescuing me. Yeah, we need to turn, I suppose, tables. Yeah. Huh? Vande Bharat first class. Yes. So in Vande Bharat first class, you can turn all the chairs around. So I should probably stop my Zoom call. Yeah, I'll help you with that. Time is of essence. Okay, so bye everybody on Zoom. I'm going to end the call.